Okay, so welcome all to week 4 tutorial for the course Essential Mathematics for Machine Learning. I am Pintu Kumar. I am a PhD scholar at IURIT Bombay. Today, more or less, we are going to cover two topics. First one is PCA, Principal Component Analysis, and second one is we'll just touch upon LD and try to solve a problem of that. Okay, so in the meanwhile, I also plan to cover some basics of mean, variance, and covariance, how to calculate. If some of you don't know by chance that how do we calculate that. Okay. So we'll try to solve one example for each of them. Okay. Okay. So first of all, what is PCA? PCA is Principal Component Analysis. Okay. 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 So first thing is that when you encounter data in real life, so you might have some features associated with it. For example, if you look at human beings, they have height, they have weight, you can look at their age, hair color, physique, what's their place of stay, okay, where are they staying, their native place. So these kind of things, like together you can club this and call it as a feature of a particular data point. Okay, but when you try to use these data points or data set for your machine learning application, not every data point or not every feature is applicable for your application. For example, let's say I want to like check whether I'll get admission in a college or not. So if you look at features like your height, your weight, those features are redundant over here. Okay, so those features are not required over there. Okay, and for you can take one more example where this PCA kind of thing helps is, let's say you have three features. One is your 10th marks. Okay, next is your 12th marks. Okay, and third one is, let's say, your combined marks of 10th and 12th. Okay. Now, if you want to like look at a data point having these three features, if you choose any two, the third one is obvious from there. Okay, so you can calculate it automatically. So explicitly mentioning that feature is not required, right? So what you can do is, many a times you can reduce size of your data. By size, I mean you are reducing number of features, not the number of data points. Okay, number of features. So these kind of techniques are called dimensionality reduction techniques. Okay, so there are two major dimensionality reduction techniques that are being covered in this course. First one is PCA and second one is linear discriminant analysis. Okay, so what is the idea behind PCA? So the idea behind PCA is to map the higher dimension data to a lower dimension space. Okay, for example, if you have let's say R10, you can map it to something like R3. Okay, so some of the advantages of PCAs are that your data has now become smaller in size, so that's why you can store it on lesser space. Second thing is, if you are able to map it into a space like R2 or R3, then your mind or we are able to visualize that data set, like how does that data look, and we can make our own inference based on that. Okay, so this is the goal of PCA, like what PCA wants to do. It wants to reduce the size, the number of features or the dimension of the data. Okay, so now let's say there can be many techniques, right, to just reduce the dimension of that. Somebody will say that I'll just pick the top two and leave rest of the elements. Okay, but choosing that kind of two-dimensional vector might not carry a lot of information about the actual data. So what we want is that we want to reduce the size and we want to also preserve the features associated with it. So we want also to preserve the information that the earlier longer vector had. Okay, so we don't want that if we are just reducing the size and that is not carrying any information about the earlier vector. Okay, so what PCA does is it tries to capture maximum information that can be extracted from that particular data set. Okay, so what is the goal of PCA? The goal of PCA is to produce a vector that carries maximum information about that original vector. Okay, so before we get into like how do we calculate a principal component and how do we take projection of other vectors on principal component. First of all, let's look at 2-3 very simple things. First one is called mean of a data set. Okay. Now, I think most of you would know this, but for example, like what kind of data you get in machine learning. So you will have some features. You will have feature 1, feature 2. Okay. And let's say feature 3. And then you will have some data points having these features. Okay. For example, if you take this as height, then first person might be me. I would write my height over here. I'll write my weight over here, and some other features probably. So this is how you create a like a data set. Okay. So one thing over here is that every row will correspond to one particular data point, and every column will correspond to a particular feature. Okay. Okay. Now, what is mean? Let's say you have some data points that you observed. Let's say it is x1, x2, and xn. Okay, you have n data point. Then what is the mean? Mean is nothing but the average of those data points. It is given by summation of xi divided by the number of data points. Sorry. Okay. So this is what, how do we define mean? Let's look at a very simple example. So the question says, Mount Rival hosts an soccer tournament each year. This season in 10 games, a person scored these many runs in every match. So in first match he scored 7, in second match he scored 5, and so on. So they are asking us what is the mean score of that player. Okay. So you can probably take 1 minute and give it a try. What you can find as the mean score. We'll just quickly go through mean, variance, covariance so that we all are on same page, and then we'll calculate principal components. Okay, so how do you calculate mean? You just take sum of these numbers, summation xi divided by number of points. Okay, sorry. So what is sum of these numbers? There are 10 points that we know, so the denominator would be 10. And what is the sum of number? It's 7 plus 5 plus 12, 19, 8, 27, and 5 is 32, 37, 41, 42, and 5, 47. I might be incorrect. Can somebody confirm? So this is 47 by 10, which is 4.7. So this is the mean score. Okay, yeah. So this is how we calculate mean. Mean is just the average score that somebody scores. Okay. Now, I'll just take a very simple example. Let's say you have 3 data points. Okay. One is minus 10, 0, and 10. Okay, this is one data set. And another one is, let's say, minus 2, 1, and 1. Okay. So now if you look at these two sets, both of their means are 0. Okay, they both have mean 0. If you take their sum, you will get 0. But there is something about this data set that this particular mean is not capturing. Okay. So if you want to represent this data with a number, let's say you want to represent this with the mean of this data set, then it is not capturing the variation that this particular data set is having. So the difference between minus 10 and 10 is 10, and over here between 0 and 10 is also 10, and between minus 10 and 10 is it's 20, right? So the points are very far apart in this case. Whereas if you look at the second case, the points are quite close to each other. Okay. So to capture this kind of phenomena, like how far or how close points are, we come up with something known as variance, or there is another tool that is used to calculate this how far the points are, called standard deviation. Okay. So what is variance? Variance, what will variance capture? Variance is denoted by sigma square. So it is denoted by sigma square is nothing but 1 upon n, okay, summation xi minus mu whole square. Recall that mu is your mean. So mean is represented by mu. Okay. So this is the formula for variance, that it is xi minus mu whole square. Okay. So and what is standard deviation? Standard deviation is nothing but square root of variance. Okay. So these are just very related terms. If you calculate one, you know the other. Okay. So what this term is capturing, you are just capturing this how far every point is from the mean. Okay, and then you are taking average of that. Okay. One more thing, very small thing over here. You might have noticed in the lecture at many a place while calculating covariance or variance, at some places R has divided by 1 by n, multiplied by 1 by n, and at some places he has divided by n minus 1. Okay. So in statistics, when you divide by 1 upon n minus 1, you get an unbiased estimator for variance, and when you divide by 1 by n, you get a biased estimator. So both the formulas are logically correct, but people generally use 1 upon n minus 1. So if you replace this formula by 1 upon n minus 1, xi minus mu square, this is an unbiased estimator. Okay. So here is an formula. Yeah. So here is an formula, question, which is asking you to calculate the variance of this particular data set. Okay. We'll probably not do this. Maybe what we can do is we can calculate the variance of these two sets that we had. Okay. We know that their mean was 0. So let's calculate variance for the first one. So this sigma square is, I'll use 1 by n, let's say. Okay. So this sigma square is xi minus mean, that is 10, this is 100, plus 0 plus 100. Okay, so the variance is 200 by 3. And for the second case, what is the variance? Variance is 1 by 3 again. This is 2 minus 0, this is 4, plus 1 plus 1. This is 6 by 3, that is 2. See how much difference is there in terms of variance. Okay, but mean was saying that these two are same quantity. Yeah. Okay. Okay. Now, whatever points that I said, for if you look at these examples, for every data point, the vector that you had or the features that you had was only one. Okay. So if you look at this 273, these are individual data points, but now you have only one features in every data point. But in real life, what you get is you have many feature vectors. Okay. So let's say you have a data set, let's say with features x1 and y, x and y. Okay. And then you have corresponding data points, maybe a1, a2, this is 1, 2, 3, 4. Then you want to know how well are x and y related. Okay. So you want to check whether x and y are like supporting each other, or they are sort of contradicting each other, or are they zero? Okay. So what is this covariance? Covariance captures the relation between two random variables or two features, and its formula is given by, so this is 1 by n. Okay. Again, you can use 1 upon n minus 1 over here. Okay. Summation of I is equal to 1 to n xi minus mu of x, so mean of first one, multiplied by yi minus mean of second one. Okay, so you are just multiplying these two and then taking their sum. Okay, so this is something that is called as covariance. Okay, now one small comment about covariance. So there is a sort of term related to covariance known as correlation. Okay, so that you can define a correlation by covariance of x comma y divided by, I think it's variance or standard deviation, I am not able to recall. Let's say it's standard deviation. I might be wrong here. This might be standard deviation. You need to confirm. So this is called correlation. Okay. Somebody has something to say?
It's standard deviation.
Then it's right, I guess. Yeah. So based on a symbol of your correlation, you can infer whether two features are like what are the relation between two features. Okay. So if it is greater than 0, greater than equal to greater than 0, then your two features are positively inclined. Or that means if one of your features increases, then the second one also tend to increase. For example, the way your height and weight are correlated. Okay. So if a person is tall, then it is most likely that he'll have a larger weight. Okay, because of his height. Okay. So these are some correlations. Okay. Now if it is less than 0, then they are sort of negatively correlated. Okay. So like if it is let's say the I'm not getting example, but that means that if one of your parameters increases, then the second one tends to decrease. Okay, so that is what is meant by negatively correlated. And one more thing, this value would be between -1 to 1. So as close as it is to 1 or -1, the stronger is the correlation. So if it is close to 1, then it is very strongly positively correlated. Okay. Now for the case when your covariance is 0, you can intuitively think that these two features are sort of independent, but there are cases when they need not be independent. Okay, so there are cases where they need not be independent, but for generally for most of the cases they are sort of independent. Okay, so I think there is a question also based on when your covariance is 0. So the point that I want to make is that when your covariance is 0, then your features need not be independent. Okay. So I think you can prove, I can give you an counter example also. I'll try to cook an counter example. Let's say you have, okay, anybody over here who is not comfortable with random variable? So if I write some random variable, he would be confused with it. Okay, then probably I'll skip, but just remember that when your covariance is 0, then you do not have these two features to be independent.
Sir, please explain random variable.
I think random variables would be covered in further lectures. So at that point we can discuss. Okay.
Okay, sir.
Okay. So my example actually involved a random variable. That's why I asked. Okay. Okay. Now we can try finding covariance of this example. Okay. So we have some x and y. So what was the formula? This was summation I is equal to 1 to n x minus mu x, y minus mu y, and divided by 1 upon n. Okay. So what is mean of x over here? So mean of x would be 1 plus 3 divided by 2. That is 2. What is mean of y? Mean of y is 3. Okay. So now if we look at the covariance, okay, what is the covariance? Covariance is 1 upon 2, that is 1 upon n, then we will sum. So x minus mu x, okay, so what is my x minus mu x? This is 1 minus 2, this is minus 1, times y minus mu y, this is again minus 1. Okay, now plus you will have 3 minus 2, this is 1 multiplied by 1. Okay, so what is the value you will obtain? This is 1 by 2 times 2. This is 1 that you are obtaining. Okay, so the covariance between x and y is 1 over here. Okay, so it is positively correlated. You can see that if your x is increasing, that is resulting in your y being increased. Okay. Okay. Now this covariance we define for two variables. Okay. Now, if you have, let's say, more than two or more than two features, let's say you have 5 features, then we capture this covariance information in form of a matrix. That matrix is called as covariance matrix, okay, and denoted by this sigma kind of a symbol. So what is its first element? Let's say you have some features x1, x2, x3, and so on till xn. Then the first position is given by covariance of x1 with itself, okay, covariance of x1 with x1. The second position is covariance of x1 with x2, okay, and this is covariance of x1 with x3, and so on, right? And downwards you can have covariance of x2 with x1. So this matrix that you get is a symmetric matrix, okay, and so on. So this is covariance of x2 comma x2. Yeah. So this kind of matrix you call it as an covariance matrix. Okay. Any doubt in this till now, whatever we have covered?
Sir, on your covariance matrix is always given or we have to create it.
So you might be given your data set, okay, and then you might be asked to calculate the covariance matrix if you talk with perspective to exams, or you might also be given some covariance matrix and might be asked some questions related to PCA on top of covariance matrix, okay. But when you look at applying these methods to your machine learning algorithm and those kind of things, then you won't be ever given covariance matrix. Covariance matrix will never be known to you. You will only have data set and you will have to compute the covariance matrices. Okay, can you please
Excuse
mute
me,
yourself?
sir.
Yes.
Excuse me, sir.
Yes.
The diagonal elements of the covariance matrix are variances.
Yes. So covariance of x comma x would mean that it is variance of x1.
Sigma square.
Sorry, yeah. So if you look at the definition of covariance, this was xi minus mu x into y. So if you just replace the same thing, this would be xi minus mu x whole square, right? 1 by n. So this is nothing but your sigma square, right? This is the formula for your sigma square. Thank you for mentioning.
And someone asked whether covariance will be given. To calculate covariance in Python, there is a direct command.
Yeah.
Thank you.
So because this machine learning community is growing this fast, so while coding, you need not worry about calculating most of the things. So almost you have packages and commands for everything. So even the papers that are published last year or last to last year, people have also coded them and compiled it in form of a library. So most of the machine learning applications would be like this only, that you will have coding won't be that difficult for you. Actually, you will have ready to use functions available with you. It's the training and other things, hyperparameter tuning, those kind of things that takes time or expertise. Okay. So now this is one example very similar to what is given in your assignment. So you are given a data matrix C, okay, and you have been asked to find its covariance matrix. Okay. Now one very small thing, if you have a matrix such that their row sum is 0, sorry, column sum is 0, that is, let's say this was x1, this was x2, mean of x1 is 0 and mean of x2 is 0, then you can straight away calculate the variance matrix using this formula. Again, this can be also 1 by n, okay. So this can be calculated by C transpose x. If you neatly write it down, you will see that this thing actually becomes the same formula for mean 0. Even for the matrices where you don't have mean 0, what you can do is you can calculate the mean for every column and then subtract that mean from every element. That way you will reach to a matrix that will have mean 0. And this is actually used in practice when you tackle real life data sets, you normalize those kind of data sets. Okay. So now for this example, so this is C, again really search. So how do you calculate the covariance matrix? You just need to do C transpose C and divide it by 1 upon n minus 1. Okay. What is n over here? N is 1, 2, 3, 4. N is your number of data points, that is number of rows. Okay. So let's calculate C transpose C. This is minus 1, minus 3, 3, 1. This is 2, minus 2, 1, minus 1 times again 1 minus 3, 3, 1, 2 minus 2, 1 minus 1. So you can calculate alongside me. So the first element is this would be 1 plus 9. This is 10. Again, this is 20. Okay, the second element is minus 2 plus 8. If I make some calculation mistakes, please let me know. Minus 2 plus 8. So, okay, sorry. This is minus 2 plus 6, that is 4. 4 plus 3, 7, minus 1 is 6. I guess I'm correct. Okay. So, now this way also, this is minus 2 plus 6. This is again 6. Okay. And this one would be 4 plus 4, 8 plus 2, 10. Okay. Now, if you just divided by 1 upon n minus 1, what you will obtain is, so n over here is 3. So this is 20 by 3. This is 2, 2, 10 by 3. Okay, so this is how you can obtain the covariance matrix. Okay. Just give me a minute. We'll just move to this principal component analysis. Somebody is joining. Just a second. We are good. Okay. Okay. Now, I won't be discussing about the proof or the derivation for principal component analysis, as the professor already has done more than justice to that. Okay, he has derived it step by step. There is no point repeating the same thing over here also. Okay. So, what I said is, in principal component analysis, what we try to do is, when we reduce it to a lower dimension, we try to capture as much information as we can in the lower dimension. Okay. So, principal component analysis gives, so this principal component gives you a way to calculate that particular vector. Okay. So, what you will do is, I'll just start with an example. Let's say you have a 2D plane. Okay. And you have some data points here. Okay. And you have some other data points here. Okay. Now, what do you mean by reducing it to one dimension? Okay. What it means to reduce to one dimension is, let's say this is a 2D set. You drew a line and took its projection on this 1D line. Okay. So this X was projected here, this was projected here. Similarly, your green points are projected here, here, 2 points here, and 2 points here. Okay. So, taking, so mapping this to a lower dimension means that you are projecting your data point to a lower dimensional space. Okay. So, in case of 2D, if you want to map it to a one-dimensional object, what do you need to know? What you need to know is, you want to know the vector or the equation of this line, so on which you are projecting this particular all your points. Okay. So when you ask the question that how can we get maximum information when we are projecting, when we are reducing our dimension, the better question to ask is on what vectors should we projecting our points so that we preserve maximum information. Okay. Now, if this was your R3 and you wanted to project it to R2, then what you would have asked is, what is the best plane on which I can project my data points so that I preserve maximum information? Now, how can you define a plane? A plane can be defined by span of two vectors, right? So again, the question can be asked, what are the two vectors on whose span, if I can project it, then I'll preserve the maximum information. Okay. So the point of principal component or the principal component analysis. So principal components are those vectors on which if you project your data points, you preserve maximum information. Okay. So the job of principal component analysis is to find, so let's say you have some Rn dimensional data point. If you want to project it to some Rk, okay. So the point is that you have to find k vectors on whose span if you project this point, then you are good to go. Okay. So that's the whole question. Okay. So what are those k vectors that you can obtain? So that is very elegantly given by this principal component analysis. So let's say you have a data set having features x1, x2, so on till xn. Now we'll talk, whenever I say n, that means this is the dimension of your original space. Whenever I'll say k, that would mean that it is a reduced dimension. Okay. So let's say you have a data set with n features. Okay. You want to project it into k, this thing. First step, what you will do is you will find covariance matrix for this particular data set. Okay. So let's say you obtain the covariance matrix. Okay. Next step would be to find eigenvalue and eigenvector for your sigma or the covariance matrix. Okay. Now, if you remember, your covariance matrix is a symmetric matrix, so you will get all the real eigenvalues and all good kind of things. Okay. So now what you will do is, let's say you want to project into k dimensional space, you will pick k largest eigenvalues. Okay. And the vectors corresponding to these k largest eigenvalues will be your principal components, or the k vectors that you were searching on whose span you can project your data points. Okay. So what you need to do is you just need to find the eigenvalue and eigenvector of your this covariance matrix, and then pick the k largest eigenvalues, and the corresponding eigenvectors will be your principal component. Any doubt in this? How do we find principal component? Why do we compute principal component? How to find
We have to make the covariance matrix for RN space.
so you manually need not do, Python will do it for you.
Yes.
Okay.
Sir, in exam we have to calculate all these things using Python.
No, in exam I don't think you will be given Python, but the questions will be as such that you don't have to do very complex calculation. And the
Okay,
matrix,
means it will be solved by manually.
I think it will be solved manually, but the matrix will be maximum 2 by 2 or those kind of things.
Oh, okay, sir. Which can be solved in a given time. Okay.
Okay.
Thank you.
Okay.
Sir, is our covariance matrix symmetric?
Covariance matrix is symmetric. If you look at the structure, so covariance of x1 and x2 is same as covariance of x2 and x1. So this
Okay.
counts as symmetric. Okay. Now, how we started all this thing was, we had some data points, let's say in Xn, okay, in Rn, and we wanted to project it into some Rk data set. Now we have k vectors, okay, k vectors, but what is the length of these vectors? Length of these vectors is n cross 1 only. The size of these vectors will be n cross 1. So your this sigma is an n cross n matrix, okay. So if you look at its eigenvector, it will be n cross 1, okay. So now you have k n cross 1 vectors, okay. How do you obtain the map of this thing in Rk? Let's call it X, this tilde thing. What you can do is, to obtain the first component, okay, you can take its dot product with the first, so these k vectors that you got, if you name them P1, P2, Pk, principal component 1, principal component 2, and so on. So the first position would be P1 transpose X, okay. Second position will be P2 transpose X, and so on. So this way you can get a k-dimensional map of any of your data points, okay.
Sir, explain again.
Okay, so we also have an example, but I'll try to explain, okay. So what was your goal? Let's say you have a two-dimensional set. You want to map it to a line, okay. So let's say you want to map this particular point to this line. Now, what you will be interested in? You will be interested in knowing where will this point be mapped, okay. If you reduce the dimension, you are interested in knowing where this point is getting mapped, okay. Now, after you have obtained the principal component, you have obtained k principal components. How will you obtain this X, this tilde? For the first component, you will do a P1 transpose with your X, okay. So for example, if this is 2 cross 2, let's say this is 1 comma 0, and you obtain P1 to be, let's say, 0 comma 1, then what is X transpose P? This is 0, right? So this X would be mapped to 0. Now if I had 3 vectors over here that we will cover in example, then we would have calculated also the second component, and so on.
Sir, in PCA we always reduce any
Any?
first given matrix to a line, 2D plane or 3D plane.
You can reduce to 2D, 3D, or any lower dimension based on your use or application.
Okay.
Okay. Okay. Okay. You can mute yourself. Can you please mute yourself?
Sir, I wanted to ask something.
Please.
So, sir, as above you explained, so we can have multiple principal components.
देखो.
This P1, P2, P3.
Yeah, what will happen is, so if you want to reduce it to, let's say, from n dimension to some k dimension, then you will take k principal components. Okay, so you can get as many as n principal components, but it depends on you how many principal components you want. So what are these principal components? Actually, if you look at how we talked just now, so these are just eigenvectors of your matrix sigma. So they are available in n number. Okay, so you have n of your eigenvectors because this is a symmetric matrix. Okay, so you will have n eigenvectors. You, for your application, if you want to, let's say, reduce it to some Rk only, you will take the first k eigenvectors depending on the value of eigenvalue. So for example, let's say you got eigenvalue as 3, 4, and 8. Okay, this is just a fictitious example, and you have P1, P2, and P3. Okay, and you want to reduce it only to a two-dimensional space. Okay, then you will choose these two, 8 and 4. So you will choose P2 and P3 as your principal component. Am I clear now?
Yes, sir. So basically, going to lower dimensional, we take the largest values.
We take the vector corresponding to largest eigenvalue.
Yes.
Okay, thank you. Okay, so now we will do one example. Okay, so we are already given with, I think there is a similar question in assignment also. So we are given with two principal components already, that we know that we have two principal components P1 and P2. Okay, now they are asking us, so if we converted our 3D space to 2D, where would the point 1, 2, 3 map to? Okay, so as I mentioned, what we will do is, so let's call this point as x. So x tilde, that is the map of x, is P1 transpose x and P2 transpose x. So let's calculate P1 transpose x. So this is 1 by root 2 plus 0 minus 3 by root 2. So this is minus 2 by root 2, which is nothing but minus root 2. Okay. What is the second component? This will term 0 minus 2 by root 2 plus 3 by root 2. This is 1 by root 2. So this is where this point gets mapped to if you do the dimensionality reduction. Okay. So I think in the assignment you have only one vector, and you have to find the map of that data point. You don't need to do anything. You just need to take the dot product. Is whatever I've like talked about till now, is that thing clear? Any doubt with anyone? Okay. So yeah, there is one more thing. So we from the beginning are saying that if we use PCA, what we try to do is we try to preserve HML's information as much we can. Okay, but if we have to quantify how much information we have preserved, that can be given by this formula. Okay, let's say you are reducing from some R5 to R3. Okay, so this is formula for Rn to Rk. This is lambda n if it is not clearly visible. So now you will have your sigma matrix of size 5 cross 5, because this is a map from R5 to R3. Okay, so your original data set is in R5. Now because this is a 5 cross 5 matrix, you will have 5 eigenvalues. Okay, but you need only top 3. Okay, so let's say this top 3 are lambda 1, lambda 2 and lambda 3. Okay, and the complete set of eigenvalues are lambda 3, lambda 4, lambda 5. Then if you put this in this formula, that is modulus of lambda 1 plus absolute value of lambda 2 plus lambda 3 divided by sum of absolute value of all the lambdas, this sort of gives you an quantization or quantity, that is your amount of information that is preserved. Okay, if you multiply it by 100, you get it in terms of percentage. Okay.
Sir, small doubt. Is it audible, sir?
You are audible.
In the case of covariance matrix, it is a PSD. I mean the positive semi-definite. That's the case. All the lambdas will be the positive only. No, why you are taking the absolute?
You are correct. So I just wrote what a professor has written. Yeah, if it is positive semi-definite.
Yeah, I got confused that also. That time also I got confused. Why it is? That's why I'm asking now because I can't ask there. That's the reason.
Yeah, if it is positive semi-definite, you will always get a positive lambdas only.
Correct, sir. Yeah.
Yeah, you're correct.
Thank you.
Okay, thank you. Okay, so
Sir, can the question be repeated once again?
so he was asking.
Satish Sethi.
I'll tell what he was asking. So he was asking that if we have our covariance matrix, so the covariance matrix is positive semi-definite. Okay, it is always positive semi-definite. When you have a positive semi-definite matrix, then all your eigenvalues are greater than equal to 0. Okay, so if my lambdas are already greater than equal to 0, why are we taking positive this modulus sign in this? Okay, so that's what his question was. Okay, so
Yes, sir.
okay.
Thank you.
So we'll move ahead. So this is sort of a full-fledged example. We'll try to solve it as as much as the calculation permits. Okay. So you are given with a data set. So you have some features x, y. Okay. And the x and y coordinate for every point is given. So 3, 5, 4, 3, and so on. Okay. Right. So this is given to you. 5, 6, 6, 7, 7, 8. Right. Now, what you need to do is, first step is to find, somebody is joining. Let me just admit that person. I think that person. Okay. So first thing is that we need to find the covariance matrix. Okay. Now, if you look at this example, here the mean is not 0. Okay. So first step would be to find mean of x1 and x2. Okay. So what is the mean of x1? This is 2, 3 plus 3, 5 plus 4, 9, 5, 9, 5, 14, 20, 27. How many points are there? 1, 2, 3, 4, 5, 6, 27 by 6. Okay. And can someone tell me what is the mean of y thing?
30, sir.
The sum is 30 or the mean is 30?
Sum is 30.
Okay. So the mean would be 30 by 6, which is 5, right? So the calculation has already started to become non-trivial. Okay. So what should be the next step? Next step should be, okay. So next step will be to subtract the mean from every data point. Okay. So for example, this 1 would become 1 minus 5, which is minus 4. This would become 1. This would become minus 2 and 1, 2, 3. Okay. So now I'm not sure I'll do all the calculations. So what I'm saying is, after you have obtained the mean value, you will subtract it from the corresponding column, and then you can use the formula 1 upon, so let's say this is matrix C, then you can use 1 upon n minus 1 C transpose C to obtain your covariance matrix. Okay. Now, after you obtain your covariance matrix, you will find its eigenvalues and eigenvector to compute the so to decide upon your principal components. Okay. So for example, in this case, you will get a 2 cross 2 matrix. Then you will pick the, if you want to reduce it to one dimension, then you will pick the maximum eigenvalue. Okay. And then you can just take the dot product to obtain its map, the way we did in previous question. So what I think I can do is, I'll leave this question as it is. Okay. So you can just note the data set. What we can do is, it can be a very good exercise for all of us, that you try finding, maybe you can use calculator, or you can use the Python notebook or the formulas that was discussed in the lecture, and actually calculate the first principal component and map of some of the points. And what I can do is, I can post an exact solution of this on the discussion forum, so that you can match these two things. So what I feel is, if you will attempt this complete question on your own, then you can probably get all your doubts cleared related to PCA. Okay. So I can wait for 2 days and then I can post. I have a solution for this, so I can post it then, if this sounds okay to you. Okay. Okay. So Now this is a 2 hour long lecture, so we can just take a break for we have 2 minutes left for 7 o'clock. So we can just take a break for 2 minutes and then we will proceed to linear discriminant analysis, LDA. Okay. So I think we can begin with linear discriminant analysis. Okay. So for some of you who are aware about machine learning, so right now if you look at current scenario, there are sort of 3 or 4 kind of main tasks that people generally try to attempt in the area of machine learning. Okay. First one is regression. Okay. Second one is classification. Okay. And another one is that you generate something, for example, your GANs or this chat GPT kind of thing, where they generate some text. Okay. So these are broadly some of the tasks that we do in machine learning. Okay. So classification is sort of a very important task or the primary task that began to evolve in machine learning. So for classification, let's say you have some 2D plane. Okay. So and you have two uh, types of data. So let's say one is of type +1, another one is of type plus a -1. Okay. So now if you have this and let's say you have something like this. Okay. Uh, let's say this, and this. Okay. So now you have two different scenarios with you. If you think for a minute, which one of them will be easier for you to classify? So what you have to do is you have to think about a rule based on which you can say that any upcoming point, let's say uh, somebody asks you to what class this point belongs, let's say this point. Okay. So among which scenario will you be more confident, or you will have a easier rule to say that this point belongs to class 1 or -1? So just think for a second, which one will be easier for you? Okay. So according to me, in my opinion, I can make a rule in this case that if my point lies on right side of this line, then that belongs to +1. And if it lies on the left side, that is called -1. I can make such rule, right? So the second one is that it will be difficult over here. Okay. So here you have a lot of complications. So something like this. So this reason plus this reason I'll assign to this minus sign, and the other reason I'll assign to some 0. Okay. So this kind of data set which are sort of separated by a line, or if you have some data point in 3D, then it is separated by a plane. Okay, so where your training data can be split into two halves with help of a plane or a line, these kind of data sets are called linearly separable data sets. Okay, so and if your data set is linearly separable, your life becomes very easy in terms of classification. You can use simplest of models to classify your training points. Okay, so
So can't we divide into multiple regions?
you can divide into multiple regions, but let's say if you have linearly separable thing. Hello.
I was saying this in second case we can divide in multiple regions.
That
Like you have like two lines, so we can say the if the point is near X, so it can belongs to plus one class, and if below that line, then that it might belong to minus one class.
You can define all those kind of rules. Here we had only 4 points, then it was easy for us to say. But when we have large number of points, then particularly picking up a rule is not very good idea actually. Okay, so we kind of look for a sort of a rule or a function based on which we can say that this belongs to this class, and if it does not satisfy this thing, then it belongs to the other class. Okay, so what I'm saying is, if my data set is linearly separable, then my life becomes very easy. The only point is, if it is linearly separable, then the life becomes very easy. In practice, you won't get linearly separable data. There are many methods to solve that, and whatever you are saying, that can also be used. But what I'm saying right now is that if it is linearly separable, then my lives become very easy. Okay, is that much point clear right now?
Yes, sir.
Okay, so yeah, what is linearly separable? I'll just mention it. So if you have some data in Rn space, okay, if you can find an hyperplane, hyperplane is nothing but a n minus one dimension plane. Okay, so for example, in 2 dimension you had a plane. If you imagine it in 3 dimension, it is a 3 dimensional hyperplane. Okay, so 3 dimensional hyperplane is difficult to imagine because we can imagine only up to 3 dimension, and 3 dimensional hyperplane would sit in 4 dimension. So that is not possible to imagine. So if you can separate your two classes using an n minus 1 dimensional hyperplane, then your Rn is then your data set is called linearly separable. Okay, that thing I think is clear. Okay, now one problem that this principal component analysis faces is, even if you have linearly separable data, let's say you had plus, okay, and this is minus. Okay, so even if you had linearly separable data, and let's say you projected it on this particular surface, then you will have plus here, plus here, plus here, plus here, plus here, and now you will have minus here, and minus here, and minus here, here. Okay, on this line only. So now you can see in this small region, your data is no longer linearly separable. Okay, so what I said earlier was that if I have linearly separable data, then my life is very easy. I have a lot of luxury. So if I already had some property which was very useful to me, then if some dimensionality reduction technique is just removing that property from data set, then that might not be very useful for me, right? Principal component analysis might be useful in some scenarios, but if in some cases it is just merging even the linearly separable data, then it is not a very good property, or it is a large drawback of principal component analysis. Okay, so to remedy of this drawback of principal component analysis, what we have is something called as linear discriminant analysis. Okay, so the idea behind linear discriminant analysis is, if you have some linearly separable data in Rn space, even when you project it to Rk space, you try to preserve the linear separability. Okay, there we used to preserve the maximum information that can be captured. Here what you try to do is you try to preserve as much, so you try to maintain the linear separability and then preserve as much information as you can do. Okay, so yeah, so there is a like straight away formula that you can use to find the component. Again, this LDA will also give you vectors or the component or the principal component. Okay, so they will just give you the vectors whose span will be the optimal line to project your data points on, similar to this PCA. So these are just two techniques to obtain your vectors. Okay, so how can you obtain your vectors now? Your vectors can be obtained by this formula. So let's say you have 2 points, two features x1 and x2. Okay, so uh, yeah, so let's say this is x1 and x2, then mu1 is your mean of x1. Okay, and mu2 is your mean of x2. Okay, so then you can calculate these principal components via this particular formula. That is, there is a matrix SW inverse. We'll get to it. How do we calculate SW? Multiplied by mu1 minus mu2. Okay, this is how we obtain. Okay, so I think I have, yeah.
Here SW stands for.
Yeah, I'll come to what SW stands for. I have made a blunder over here. Let me just correct myself. So I'm really sorry. So this mu over here means something else. So let's say you have some data points. Okay. Now let's say you have some x as well as some labels now, which are called as yi. So if you look at this motivation, so this had some +1 label, some -1 label associated with it. Okay, so this have some labels with them, right? Now what you do is you form two classes using it. Okay, so you form two classes using it. So the first class, let's say you call it class 1 and let's say you call it class 2. Then the mean of elements of first class is denoted by mu1. This mu1 you will get as a vector. We will solve one example, then you will know that mu1, whatever you obtain, is a vector. So this is mean of features of first class. This is for a two class problem. So you can have n features. Then your mean will vector will have n components, or one component corresponding to every feature. But you will take some over your the first class, that is your, let's say, +1 class. And similarly, you can obtain mu2 using your C2 class. Okay. Then now I said that this SW can be inverted and multiplied with this particular vector. This is whatever I've written over here is formula for SW and not for SW inverse. Okay, so this is SW is given by S1 plus S2. Okay, and this is xi minus mu1. Okay, so you will have first data point containing n features, let's say, then this will be also a vector, minus mu1, that will also be a vector. So this is this whatever quantity you will obtain is a vector. You take its dot product with its transpose. So if you have this vector and you take its dot product with something like a row vector, then you will get a matrix. You won't get a single point. Single point you would have got if you would had a row vector multiplied with a column vector. Here you are forming a matrix, and then you take sum of such matrices. Okay, and similarly you do it for second class, then you sum them up and you call it as SW. So you were asking what is SW. SW is a just a notation. This is, I think, called as in-class covariance, I guess. Yeah, this is within a class you are finding something like covariance. Okay, I am not very sure about terminology. Sorry. Yeah. So we'll straight away look at an example. Okay. Yeah. So as I said, there are two classes. They are calling it as class 1 and class 2. Okay. Now points are also linearly separable if you look here. Okay. So they are asking us to find linear discriminants. Okay. So first of all, we will try to find mu1 and mu2 because that is important. And then we will go to that thing. Okay. So what is my mu1? Mu1 would be, there are 1, 2, 3, 4, 5 points. So this is 1 by 5 times summation of xi's. So this is x11, x12. Okay. So I'll just sum this up. This is 4, 2 plus 2, 4. Okay. Plus 2, 3 plus 3, 6. These are feature. This is one data point. This is second data point, right? Plus 4, 4. So if you look at this, this would be 4 plus 2, 6 plus 2, 8, 3, 11, 4, 15. So this is 1 by 5, 15. Second component is 6, 9, 15, 4, 19. Okay. So this is 3 and 3.8. This is the value of mu1 that you will get. Okay. Similarly, you can try finding mu2. So I won't write the complete formulation. We can just sum over here. 9, 6 is 15, 9, 24, and 8 is 32, 42. So 1 by 5, this is 42. This is 18, 5, 23, 30, and this is 38. Okay. So yeah. So this is the mean that you get for mu2. Okay. So yeah, I'll just calculate one of these S1 and S2 also, so that you know how to calculate this S1 and S2. Okay. Now, yeah, I'll probably push it down. Yeah. So what is my S1? S1 is given as summation xi belonging to class 1, xi minus mu I, xi minus, sorry, this is mu1 transpose. Okay. So for the first one, my x is given to be, okay, this is down. So x is 4, 2, and what is my mu1? Mu1 is 3.8. Okay. So what is this? So this would be 1 and minus 1.8. Okay. So what would be the first component? This would be 1 minus 1.8 times 1 minus 1.8. What do we obtain? This is 1, this is minus 1.8, this is minus 1.8, and this is 1.8 square. Okay. You can calculate what is 1.8 square. So this is how you will get the first component. Similarly, if you will take the second data point, then you can calculate similarly, you will get second component, you will add to it. Similarly, for all the data points from class 1, when you sum them up, you will get a matrix called S1. Okay. Doing similar procedure for your second class, you will get a matrix S2. Okay. Now, to obtain SW, you will have to sum again S1 and S2 and take its inverse. Okay. So yeah, and then you need to multiply it with the difference in mean, and you will get your principal component. Okay.
Sir, can you scroll up to the question once again?
Sure.
Okay, sir.